important thing is to calculate electrical potential when you have continuous charge distributions. Okay, so when you have a continuous charge distribution, for example, potentials between two parallel conducting plates, what happens in that situation? So if you have two conducting parallel plates and you have an E field that goes from one plate to another, you can calculate what the potential and then in fact what the electrical field will be. So for parallel plates, delta V will be V1 minus V0, or equals to E dot dl, where dl is the small displacements between them and E is the electrical field. Now, if you have a situation where the E field is constant between the parallel plates, in that case, the E can be separated out. It can be pulled out of the integral, and integration will be from 0 to d over dx, where dx is along the x-axis, or once you integrate over that, then it becomes equals to d. This is also called the famous Mr. Ed equation, which basically says is that the change in potential is equals to E times D. So Ed. Something very important to note. So the derivation of this delta V equals ED did not require regular plates or any plates at all. It works as long as E is uniform. So in general, if you have an E field that is uniform between points that you are looking at, you can use this equation. It is a very, very useful tool. So going back to talking about different kinds of charge distributions, we have to recall our formula. So for a collection of charges, V is going to be equals to 1 over 4 pi epsilon naught, or K, equals sigma Qi over Ri. Okay? So in general, for the calc-based class, this sigma is going to be replaced by integration. So what you're going to do is when you start talking about charge distributions of different forms, you are going to say K sigma dq over R, which includes, for example, a uniform line of charge. So now this looks like a really, really complicated problem, right? And it looks really scary when you first look at it. So we're going to talk about, I'm going to show you how to come up with this expression, okay? And it's not really that hard. We've been doing a bunch of these for electrical fields, etc. So it's not going to be that hard. So I'm going to walk you through the uniform line of charge. I am also going to try to talk to you about the ring of charge, which again looks really scary, right? When you first look at it, it looks really scary, but it really isn't. And then we'll talk about a disk of charge. So let's start first with a uniform line of charge, and we are going to calculate the potential.